All right, we've looked at some straight line motion and forward and back as I've walked towards the sensor and away from the sensor with the poster board, and you can see the lines going down and up on the graphs. So let's pause for a minute before we continue with graph analysis and look at a couple of vocabulary terms that we're going to be using in our graph analysis questions. So we need to look at scalars versus vectors. All right, scalars are those things that only have size. So size only. And because they are size only, they're also only positive. They are their absolute value. There we go. Absolute value of quantities. Some examples that we're going to be using are distance, speed, mass, time. Time's an interesting one because we don't do negative time. We only start time at 0 and then count in the positive direction. So we're only ever going to look at positive times, but time doesn't really fall in either one of these categories. We just say, nope, time's going to be positive. Contrast that with vectors, which have a size and a direction. Because they have a size and a direction, they can be shown as arrows. So we can say, let's, not a fawn, let's push that way. Let's say I'm moving a big box on the floor, and here's my hands on the box, and I'm pushing the box to the right. So I can represent my push as an arrow pointing to the right. And if I push harder, the arrow gets longer. If I change the direction of my push, then I rotate the arrow around. Because they have a size and a direction, they can be negative. And the negative, all negatives do in physics and actually in math as well, is indicate direction. And they indicate that this quantity is going to point in the opposite direction. So some examples of vectors are displacement, velocity, acceleration, and push. The technical physics word for push is force. Distance and displacement are related, just like speed and velocity are related. They're not exactly the same thing because it's not just we'll take a distance and throw a direction onto it. Distance is a how far. So if we have 2 points, we've got the stairs in my house and then the front door. My son could walk over here to play with the train tracks and then go look at a book on the couch and then build something with some Duplos and then go into the kitchen to get a snack and then come out to get his shoes and then go to the front door. And he would have spent all of that, gone through all of that distance to go from the stairs to the front door. Or he could have just walked the straight line from the stairs to the front door. And that would be the displacement. So this blue line, this straight line distance, the shortest possible distance, is displacement, and it points from where I started to where I finished. The distance covered includes all of these wiggles in addition to the beginning and the end. And the same sort of idea with the speed versus the velocity. The speed is going to be including this whole distance for how fast he was moving, but his velocity is just going to be that displacement divided by a certain amount of time. All right, which brings us to average versus instantaneous. An average velocity or an average acceleration is going to be over an extended period of time. Over an extended period of time. Instantaneous is at only one point in time. So when we get to our graph analysis and start considering graphs, when we ask you for the average velocity or the average speed, it's between two distinct points in time that are spread out and apart from each other, so you're going to be subtracting the two times on the x-axis. And average speed, again, is going to come out of the, I need the word total here, total distance over total time. But the average velocity, we're going to change the distance to displacement. Total displacement over total time. And we're going to use these two guys as we look at some displacement or position versus time graphs, and consider the slopes of those graphs, the speeds of the objects being described by those graphs, and any place where you're asked for a velocity, you need to make sure that you only look at the beginning and the ending points, just like we're looking at the example of my son over here, the beginning and the ending points. But if I say anything about speed, then you're going to need to include the distances, which is how far did the object go as being described by the graph. So go take a look at those analysis questions for displacement versus time graphs.